The side of the moon we never see has been quietly keeping a secret about our own planet. And this week, two very different groups of scientists arrived at the same place from opposite directions.
One group read it out of the dirt, the other argued about who gets to own it.
Meanwhile, a rocket sits on a pad in South Texas waiting for a second chance.
And a star that vanished behind its own wreckage 25 years ago has finally stepped back into the light.
Welcome to Astronomy Daily. I'm Anna.
And I'm Avery. It's Thursday, the 23rd of July, 2026, and this is episode 148.
Coming up, Starship gets another go with a caveat. What the far side of the moon knows about Earth's magnetic field, whether that far side should be off limits to industry, a one-of-a-kind stellar explosion finally identified, and the possibility that our entire galaxy once turned over.
Plus, a Skywatch closer with some genuinely useful advice about the Delta Aquariids, which is to not wait for the peak.
Let's get into it.
We start at Starbase because today is meant to be the day.
SpaceX is targeting Flight 13 of Starship with a 90-minute launch window that opens at 6:45 in the evening Eastern Time. That's 5:45 Central and 3:45 in the afternoon on the Pacific Coast. For those of us on this side of the world, that lands at 9:15 on Friday morning Australian Eastern Time and 10:45 Friday morning in New Zealand.
So North America gets it over dinner and we get it over breakfast. For once, nobody has to set an alarm for 3 in the morning.
For once, although, and this is the part I want to be upfront about, that schedule is not locked.
Meaning?
Meaning the public schedule says today, but the road and beach closure notifications around Starbase suggest additional testing is happening on Pad 2. Those closure notices are one of the more reliable tells in this business because they have to be filed in advance and they tend to reflect what's actually planned rather than what's been announced. So there is a realistic chance this slides again.
Which would make it the third date for Flight 13.
It would. Let's recap how we got here because the arc matters. Flight 13 was first set for Thursday, the 16th of July. The countdown went all the way to 0 and then stopped. The flight software triggered an automatic abort right at T0 because 4 of the 33 Raptor engines on the Super Heavy booster failed to reach acceptable starting parameters.
And the threshold is 3.
So it missed by exactly 1 engine. That's the system working as designed, and it protected both the vehicle and the pad. Elon Musk said afterwards that 2 Raptors would be pulled and replaced before the next attempt.
That's a remarkably narrow margin between a scrub and a launch.
It is, and it's deliberate. The vehicle was cleared to fly in the first place because the FAA closed out its mishap investigation into Flight 12 on the 13th of July, and the booster had already completed a full-duration static fire of all 33 engines back on the 10th.
So the hardware had been through its paces, it just didn't like the moment.
That's about the size of it. Here's what makes this flight worth paying attention to beyond the launch itself. Flight 13 is carrying 20 V3 Starlink satellites, the next generation of the constellation, and the first time Starship has ever deployed them.
That's the whole point of the vehicle eventually, not the spectacle, the payload.
Right. Up to now, these have been test flights carrying simulators and mass models. This is the first time the thing does the job it was built for, even on a suborbital trajectory.
And the flight profile?
Booster and ship separate as usual. Super Heavy steers itself to a controlled splashdown in the Gulf about 7 minutes after liftoff. No catch attempt with the chopstick arms on this one. The ship continues on, deploys the satellites, and then comes down for its own splashdown in the Indian Ocean off the coast of Western Australia at around 65 minutes.
Which is worth flagging for our listeners in Perth and along that coast. You are not going to see it from the beach. It's a long way offshore, but it is your patch of ocean.
It is. And for anyone in North America hoping to catch the launch itself, it's a star-based departure, so the viewing sites around Boca Chica and South Padre Island are the ones that matter.
So, assuming it goes.
Assuming it goes. If you're listening to this on Thursday, check before you commit your evening. If you're listening later, you already know how it turned out, and we'll pick up the result in the next episode either way. This arc has taught us not to get ahead of ourselves.
Now to the moon, and to something I find genuinely lovely about this next result, which is that it turns lunar soil into a record of Earth.
Don't I?
The sun blows a continuous stream of charged particles out across the solar system, the solar wind. The moon has no atmosphere and no global magnetic field to speak of, so those particles hit the surface directly and bury themselves in the soil. Over billions of years, the regolith becomes an archive of everything that struck it.
And noble gases are the good bookkeepers.
Exactly. Helium, neon, argon, krypton, xenon. They don't react with anything, so whatever went in stays in, and how deep it went tells you how fast it was traveling when it arrived.
So what did they find?
A team at the Chinese Academy of Sciences Institute of Geology and Physics analyzed samples from Chang'e 6, the mission that returned material from the far side, from the South Pole Aitken Basin. That's 1,935 grams of soil, just under 2 kilograms.
And that's the first far-side material anyone has ever had in a laboratory.
Every previous returned sample, Apollo, Luna, Chang'e 5, came from the near side. So this is the first time anyone could directly compare the two hemispheres. They worked through 7 portions using stepwise heating and laser extraction, measuring the isotopes of all 5 noble gases. And the far side soil is measurably different. The solar wind went in faster and went in deeper.
Deeper meaning higher energy.
Higher energy, yes. The clearest signal was in neon. The ratio of neon 20 to neon 22 in the Chang'e 6 material sits below anything recorded in any near-side sample, which points to stronger processing on the way in. And the heavier gases, krypton and xenon, come out of the sample at different temperatures than they do from Chang'e 5 material, which is another way of reading implantation depth.
So why would the far side get hit harder?
Because we're in the way. Earth magnetosphere. As the moon travels around its orbit, it spends part of each month downstream of Earth. Inside the long magnetic tail are planet trails behind it. And in that region, the solar wind gets slowed down before it reaches the lunar surface. But it's the near side that's facing us, so the near side is the one that catches at the accelerated wind. The far side is permanently turned away and takes the full, unmoderated stream.
Earth has been sheltering the side of the moon that looks at us for 4 billion years.
For 4 billion years. And the team put a number on it. Roughly a quarter of the total solar wind exposure at the Chang'e 5 landing site involved that slowed down flow. At the Chang'e 6 site on the far side, there's no sign of it at all.
That's a beautiful result. And I assume it cuts the other way as well.
That's the part that excites me most. If the near-side soil records how much shielding Earth was providing, then heavy noble gases in lunar regolith become a fossil record of our own magnetosphere. Combine that with the rock magnetism record on Earth, and you have a completely new way of reconstructing how our magnetic field has changed over deep time.
Which is not a small thing, given the magnetosphere is the reason we still have an atmosphere.
Not a small thing at all. The moon has been keeping notes on us, and it turns out the far side has the cleaner copy, which, as it happens, is exactly why a room full of astronomers spent Tuesday evening arguing about what we're allowed to do out there.
So this was at the Royal Astronomical Society's National Astronomy meeting, which is running this week at the University of Birmingham. On Tuesday evening, they staged a formal debate on a single proposition, that the far side of the moon should be preserved solely for scientific endeavors.
And the answer is presumably not obvious, or there'd be no debate.
It's genuinely not. Arguing in favor were Joe Silk of Johns Hopkins and Jonathan McDowell, who most of our listeners will know from Jonathan's Space Report, and who is now an honorary professor at Durham's Space Research Center after decades at the Harvard-Smithsonian Center for Astrophysics.
And against?
Nikita Chu, also at Durham, who works on space technology governance, and Manuel Salvoldi, an aerospace engineer with 25 years across industry and academia. Barton Ward convened it. The case for protection rests on one physical fact. The far side is the only radio-quiet real estate anywhere near Earth.
The moon is tidally locked, so the same hemisphere always faces us, which means the far side is permanently shielded from every transmitter, every radar, every broadcast on this planet. And that matters because
there are signals we want to detect that are drowned out everywhere else. The cosmic dark ages, the stretch of time after the Big Bang before the first star switched on, the radio emission from that era is faint and it's low frequency, and Earth is far too noisy a place to hear it. A far-side radio telescope is arguably the only way we ever will.
That's a fairly specific and irreplaceable thing to be arguing about.
It is, and Silk's framing was essentially generational, that we should protect these conditions now for science that won't be done for decades. Because the questions at stake are whether we're alone and how the universe began.
And the physical case doesn't stop at radio.
No, they also argued the far side would be an exceptional site for gravitational wave detection. No atmosphere, no weather, very little seismic activity compared with Earth, and no artificial light, which is becoming a real problem for optical astronomy down here.
So what's the counter-argument? Because leave it alone is easy to say.
The counter-argument is about sustainability, and I thought it was stronger than people might expect. Few's position was that this isn't a challenge to the value of the science, it's a question of how you keep going back at all. Lunar exploration that depends entirely on government funding is fragile. Commercial investment is what makes it resilient. And her argument was that you can have both under proper governance, that an inclusive cislunar economy on the far side doesn't have to turn into a free-for-all.
Which is a fair point. A protected region nobody can afford to reach is protected in a fairly useless way.
That's the tension exactly. And McDowell's put the stakes in the broadest possible terms. His line was, is the whole solar system up for grabs, or do we set aside reserves?
That's the real question, isn't it? Not the moon specifically.
Not the moon specifically. His argument was that whatever we decide in the next few years becomes the precedent for everything after. Mars, the asteroids, all of it.
Did they take a vote?
They did, before and after, by QR code. Support for the motion went from 68% to 76%.
So the room moved towards protection.
Which, given the audience, isn't a shock. But an 8-point swing after hearing both sides is a real result rather than a formality. And it fed into a full session the next day on lunar governance and regulation.
And in the meantime, Chang'e 6 has just demonstrated that the far side is scientifically valuable in ways nobody had directly measured until this month.
Which rather sharpens the argument.
Staying at the National Astronomy meeting, because there is a genuinely extraordinary object I want to talk about, and it lives in our skies.
Southern skies?
Puppis, which for our Australian and New Zealand listeners is well placed for a good chunk of the year, and for northern listeners sits low on the south. The object is V445 Puppis, and it is the only confirmed helium nova in the Milky Way.
Define helium nova.
So a nova, an ordinary nova, is a white dwarf in a binary system stealing gas off its companion. That gas piles up on the surface, pressure and temperature climb, and eventually you get a runaway thermonuclear explosion. It doesn't destroy the star, it just blows the accumulated layer off. And in virtually every case, that stolen material is hydrogen-rich, because hydrogen is what stars are mostly made of.
And this one isn't.
This one has essentially no hydrogen at all, which is a very strange thing for a stellar explosion to be missing, given hydrogen is the most abundant element in the universe. So the obvious question is, what is it stealing from?
And nobody could see.
Nobody could see. V445 Puppis erupted in late 2000, and it threw out an enormous bipolar outflow. 2 lobes of material streaming in opposite directions, more than 1 trillion miles across. But the eruption also created a thick disk of dust that completely swallowed the system. For more than 20 years, astronomers could watch the debris expanding, but they could not see what was inside it. The dust has now thinned enough. John Mills, a researcher and PhD student at the University of Warwick, put together observations spanning 2 decades to finally see through.
Using what?
A stack of instruments. Infrared from the Very Large Telescope in Chile, optical imaging from Hubble, long-term spectroscopy from the Southern African Large Telescope, and photometry from TESS. And the answer is a white dwarf feeding off a helium star.
And a helium star is?
A star that has been stripped of its outer hydrogen envelope, most likely by the companion it's now feeding. They are genuinely rare. The estimate is a few thousand stripped helium stars among the hundreds of billions of stars in the entire galaxy.
So one of the rarest kinds of stars, in the only known example of one of the rarest kinds of explosions.
And it's already loading the gun again. The system is actively transferring material once more. The two stars orbit each other every 3.7 days, which is around twice as long as anyone previously thought.
You said there was a mystery.
The bullets.
The bullets.
Embedded in the outflowing debris are discrete clumps of gas, possibly oxygen-rich, though the composition isn't nailed down, moving at up to 20 million miles an hour. That's roughly 9,000 kilometers per second, around 3% of the speed of light.
And nothing like that has been seen elsewhere?
Nothing like it in any other nova anywhere. Mills suspects they formed after the outburst rather than during it, but as he put it, their origin is a mystery.
Which is the honest answer, and I appreciate that he said it.
So do I. Now, the reason this matters beyond its own strangeness. Astronomers suspect that repeated helium-rich eruptions on a white dwarf might be one of the pathways that eventually produces a Type 1a supernova.
And Type IAs are the standard candles.
They are. They explode with remarkably consistent brightness, which is what makes them useful as distance markers across the universe. They're how we measured cosmic expansion, the work that won the Nobel Prize for the discovery that the expansion is accelerating.
So the ruler we use to measure the universe depends on understanding how these things detonate.
It does, and whether helium novae actually get there is still an open question. But V445 Puppis is now the clearest laboratory anyone has for testing it. And it took 25 years of dust clearing to get the door open.
Last story before we look up, and it's the biggest one in terms of sheer scale. There's a case being made that the entire Milky Way once flipped over.
Flipped over how exactly? Because a galaxy doesn't have a right way up.
It doesn't, and that's the right instinct. What's being proposed is a change of orientation, that the disk of our galaxy reoriented itself by more than 90 degrees relative to the halo of old stars around it.
And what put that idea on the table?
A puzzle that's been sitting there since Gaia. Our galaxy has a flat disk where most of the stars live, and around that, a much larger, much sparser stellar halo, mostly stars that formed in smaller galaxies and got absorbed when those galaxies were pulled in.
Debris from past meals.
Essentially. And Gaia showed that the halo barely rotates. It creeps around at something like 10 to 20 kilometers per second. The disk, by comparison, is moving at about 220.
That is a very large discrepancy.
It is, and nobody had a satisfying explanation. So Kirill Batrikov at Durham went looking for one in simulations, the Auriga suite, which models Milky Way-like galaxies in detail. He took 25 of them and followed their evolution across roughly 11 billion years.
And?
The galaxies that ended up with the most slowly rotating halos had two things in common. They'd experienced a major head-on merger, and their disks had reoriented by more than 90 degrees.
And we know we had a major head-on merger.
We do. Gaia, Sausage, and Enceladus, the collision roughly 10 billion years ago that dumped an enormous quantity of stars into our halo and is the reason the halo looks the way it does.
So the proposal is that the same collision exerted a gravitational torque on our disk and slowly turned it over inside the surrounding dark matter halo.
Slowly meaning over hundreds of millions of years. Nothing about this was sudden, but the end state is that the plane the sun orbits in today may bear no relationship to the plane stars were orbiting in before the collision.
That does something odd to my sense of place.
It does mine too. And I want to be careful here because Batrikov himself is careful. His position is that a disk flip is a likely explanation given how slowly the halo turns, but that it's too early to claim it with full confidence. What he wants is independent signatures, other scars that a reorientation on that scale should have left behind.
Is there anything pointing the same way already?
There is, and it's suggestive rather than conclusive. Separate work this year, led by Ling Zhu, used the motions of more than 600,000 giant stars from Gaia and the Lammost survey to reconstruct the shape of our dark matter halo. And the outer halo appears to be oriented almost vertically relative to the stellar disk.
Which is what you'd expect if the inner part tilted and the outer part didn't.
That's the reading. The outer halo kept the old orientation, the disk and inner halo swung round. Two independent lines of evidence converging on the same story from completely different data.
Not proof.
But it's the kind of thing that turns a curiosity into a research program. And I rather like that the biggest structural question about our own galaxy is one we can only answer by looking at it from the inside.
Right. Time to look up. And Anna, we have actual advice today rather than a countdown.
We do, and the advice is don't wait for the peak.
Explain.
The southern Delta Aquariids are running now. The shower is already active, and it stays active into late August. The American Meteor Society puts maximum activity around the 30th of July.
And the problem with the 30th is the moon.
The moon is the problem. Full moon falls on the 29th of July, so on peak night, you're looking at a sky that is something like 98% illuminated. That will wash out most of the shower because Delta Aquariid meteors tend towards long, graceful trails rather than bright fireballs. They're exactly the kind that moonlight erases.
So the peak is the worst night of the run.
Close to it. But here's the good news. This shower has no sharp maximum. It rambles. Rates build slowly and stay roughly level for well over a week, which means the mornings between now and about the 27th are better than peak night because the waxing gibbous moon still sets before the radiant gets high.
So the window is after moonset before dawn.
After moonset, before dawn. That's your window, and it applies wherever you are. Where do we look? The radiant sits near the star Scat in Aquarius. The easiest way in is to find Fomalhaut, bright and noticeably alone in a fairly empty patch of sky, and work from there. The Great Square of Pegasus helps as well.
And that's a very different experience depending on which hemisphere you're in.
Completely different. From Australia and New Zealand, the radiant climbs close to overhead in the pre-dawn hours. This is genuinely our shower. The southern part of the world gets the best of it every year, from Sydney or Auckland, anywhere from about 2 in the morning until first light.
And for our North American listeners, who are the largest part of this audience,
You still get a good showing, but the radiant stays lower in the southern sky, so you'll see fewer of them and they'll come in at shallower angles. The upside of a low radiant is Earth grazers, meteors that skim along the atmosphere and leave much longer trails than usual. The best hours are the same, from around 2 in the morning local time until dawn, so 2 to 5 a.m. Eastern and the equivalent across Central, Mountain, and Pacific.
And get south-facing and dark.
Get south-facing, get away from lights, and give your eyes 20 minutes to adapt before you judge whether it's working.
One more thing, and this one is a watch this space rather than a forecast.
The sun has woken up.
Sunspot 4493.
That one. It appeared essentially from nothing over the space of a couple of days and grew fast, and it now has what's called a beta, gamma, delta magnetic classification, which is the most complex classification there is. Regions like that are where the big flares come from.
And it's already produced some.
3 M-class flares inside a single day, the strongest an M3.4, each of them causing brief minor radio blackouts across different parts of the world. Forecasters have been putting the odds of further M-class activity at better than even, with a smaller chance of an X-class event.
So it's worth keeping an eye on the aurora alerts.
It is. Earlier this week, a fast solar wind stream from a coronal hole pushed conditions to minor storm level, with aurora possible as far equatorward as Hobart in the south and Seattle and Edinburgh in the north. That particular stream is easing now, but with a region that complex facing us, the situation can change quickly.
and southern hemisphere observers have the advantage of long winter nights right now.
While northern observers are fighting short summer ones. Swings and roundabouts.
That's episode 148, Starship waiting on a window that may or may not hold, a far side that's been quietly recording our magnetic field, and an argument about whether we should leave it alone.
Plus, a star that spent 25 years behind a curtain, and the galaxy that may have rolled over in its sleep.
Show notes, sources, and everything else are at astronomydaily.io. We're at Astro Daily Pod wherever you like to find us.
If you're up before dawn this week chasing Delta Aquariids, we'd love to see what you catch.
We'll be back tomorrow. Until then,
Clear skies.